Hey everyone, and welcome. Today we are going to tackle one of those things in algebra that can be a little confusing at first, function notation. You know, that little f with an x in parentheses, f of x, that seems to be everywhere.
Okay, let's just get right into it. We've all been there, right? You see f of x, and your brain immediately screams that's f times x. Because, that's what parentheses usually mean in math. But in this case, it's something totally different, and that's the number one hurdle we're going to clear right now. This quote just hits the nail on the head. Don't think of it as multiplication. Think of it as an instruction. It's telling you, hey, take the number 2 and apply this specific rule we've named f to it. So what in the world is this rule? Let's break it down. The best way to think about a function is to imagine it as a machine, a very specific, very predictable machine that just follows one simple process. So here's the formal textbook definition. A function is a rule that assigns to each input exactly one output. And those are the two most important parts. Every input has to have an output, and it can only have one.
So yeah, let's just strip away all the jargon. It really is that simple. It's a machine. You put a number in, the machine follows its rule, and it spits exactly one number back out. That's it.
And this visual gives us a couple of those key technical terms. The collection of all the things you're allowed to put into the machine, that's called the domain. And the collection of all the possible things that can come out of it, that's called the range. So you grab an input from the domain, and you get an output in the range. Okay, so if a function is just a rule, how does f of x fit in? Well, you can think of f of x as a much more descriptive, kind of souped-up version of the simple letter y that we're used to from equations like y equals 2x plus 1. Let's make this crystal clear with a real-world example. Here's a function that describes how much Charlie earns at his summer job. His pay is based on a simple rule. He gets a flat $50 plus $30 for every hour he works. So let's break this down. We named our function e for earnings. Makes sense? The input, our variable, is t for time and hours. So the whole thing, e of t, represents the output, the total earnings for a certain number of hours. You see how much more info that gives you than just calling it y? So, how do we use it? Well, if we want to find out what Charlie earns for working 4 hours, we calculate e of 4. That notation is our instruction. Find every t in the rule and just replace it with the number 4. After that, it's just simple arithmetic. And this, right here, is where you see the real power of function notation. E of 4 equals 170 isn't just a random calculation. It's a complete story. It tells us the name of the rule we used, earnings, the input we gave it, 4 hours, and the precise output it produced, $170. It's all right there. Okay, now let's circle back to our machine idea, because we need to talk about the single most important role that separates a real function from any other old equation out there. I absolutely love this analogy. A function has to be predictable. If you press the Dr. Slurp button on a soda machine, you expect to get a Dr. Slurp every single time. If one day it gives you something else, you'd say the machine is broken. Well, in math, we just say it's not a function. This table really clarifies that distinction. You see, a general relationship is just called a relation, and it can link one input to many outputs, kind of like how one person can have multiple phone numbers. But a function? It's much stricter. Each input has exactly one output, like how a student has only one unique roll number. So what about when we're looking at a graph? How can we tell if it represents one of these predictable working machines? Turns out there's a beautifully simple visual trick for this. It's called the vertical line test, and the rule is simple. If you can draw a single vertical line anywhere on the graph and it crosses the curve in more than one place, then it is not a function. Let's see it in action. The graph on the left, it passes the test. No matter where you draw a vertical line, it only ever hits the curve one time. This is a function. The graph on the right, though, fails spectacularly. A vertical line can hit it in lots of places. That means one input would have multiple outputs. It's a broken machine. It's a relation, for sure, but it is not a function. All right, now that we have the theory down, let's apply this understanding to another practical problem and see how this all connects. Here's a new scenario. We've got a function s for Kirsten's savings over m months, but this time we're going to work backwards. We know the output we want, $800, and we need to find the input that gets us there.
To solve this, we just set the whole function equal to 800. And the algebra from here is pretty straightforward. We subtract 500 from both sides, then divide by 50, and that'll give us m.
The math gives us the number 6. But what does that 6 actually mean in our story? 6 what?
It means the input is 6 months, and for that input, the output of the savings function is $800. The notation lets us clearly connect the numbers right back to their real-world meaning.
So, to sum it all up, f of x isn't just some weird math symbol. It's a powerful tool. It's a label for a specific rule, and it's a map that clearly shows you the relationship between an input and its single, unique output.
And this brings us to a final thought. Functions are just predictable rules that govern how things are related. So my question for you is this. What are the unwritten functions you use every day? You know, the input of coffee beans that leads to the output of your morning brew? Or the input of pressing the accelerator that leads to a specific change in their car's speed? Once you start looking, you'll see these rule machines are everywhere.